Okay, conservation of angular momentum. The first thing is just that angular momentum is conserved. Now, this is in, obviously, a few situations where you have no torque, so that means an isolated system. Now, what we're going to talk about are ways that the system can change, but you don't actually have a torque on your object if it's isolated. So one of the examples of this is that you have two masses on a rod. You initially have an angular momentum, and because the rod is effectively massless, we would just consider the particle definition of angular momentum for each of these. Now, if our rod suddenly expands, this is kind of like a little rotational explosion, if you will, we now have a new radius that each of these masses is going at. Now, no external torque has been applied, so our initial angular momentum must equal our final angular momentum. However, the radius is now different, and so that means that the rotational speed is now different. So we have two individual moments. We don't really have a moment of inertia here, we're just using the particle definition. So we have two individual angular momenta. We would sum them together and say that that's my total system angular momenta initially. And we have a total system final angular momenta, and because it's isolated, the change has only originated from within the system itself. Nothing external has acted. These are then equal. So for simplicity, let's just say that m1 equals m2. So now we can combine these together and see quite simply what's going on. This is our initial angular momentum, saying that the masses are the same, and we've added them together, our final angular momentum. Note that there's a 2m on each side that cancels, and so now we're left with this, that our initial speed times our initial radius must equal our final speed times our final radius. So given that we know what our final length is, and we knew what our initial one is, this would allow us to actually solve for VF in terms of VI, our initial radius, and our final radius, where the final radius is the length final divided by 2. And so same for the initial one. So the point being that if your system suddenly moves farther from the axis, for angular momentum to be conserved, your speed has actually decreased. There hasn't been any forces applied. Well, and again, there's no torques at least applied. So this is just due to conservation of angular momentum. Now, this is a little hard to think through. You probably have never seen a situation quite like this in your real life, so you just have to believe the physics equations and you don't have any intuition. But there is a situation that you've possibly seen in real life, and that is a figure skater spinning. And the idea being that initially the skater starts spinning with, for instance, her arms and perhaps a leg spread out. So the idea being that our figure skater here has an axis of rotation and that she is spinning around it. But she also has an initial moment of inertia. Then she brings in her arms and her legs and she starts spinning faster. Why? Why does she spin faster? Well, in this case, no torque has been applied. We can approximate this as an isolated system. And so in that case, our angular momentum final must equal our initial angular momentum. And what has happened is that her final moment of inertia is actually smaller than her initial moment of inertia, right? Remember, moment of inertia is bigger the more mass you have farther from your axis of rotation. So as she brings in her body to make it as small as possible to the axis of rotation, this final moment of inertia decreases, which means since her angular momentum is conserved, her angular speed increases. So that's what's going on here. So as you change the moment of inertia, if it's an isolated system such that your angular momentum is conserved, you expect to see your rotation speed change. One last example is the collisional equivalent of a rotational equivalent of a collision. And the idea being that initially you have a disk that's spinning at some rate here, 200 RPMs, and we're dropping a loop onto it. The loop is initially not spinning. At the end, they're spinning together. Now let's think about what's going on. So we would say that this is an isolated system as long as you include all of this in your system. And so your final angular momentum must equal your initial angular momentum, right? It's isolated. But what we see is that we've gone from a moment of inertia of what's rotating, of I disk, to now this I hoop plus disk. And that means that this I final is definitely greater than I initial, right? This is harder to spin. And so we expect that our final angular speed is less than our initial speed. So let's think about this briefly in terms of torques. When this loop hits the disk, there's friction between them, and that would be in the wording of the problem. There's friction between them. So there's a frictional force that the loop, or the hoop, same thing, exerts on the disk that slows it down. There's a frictional force that the disk exerts on the loop that speeds it up and causes it to spin. This is a Newton's third law pair. This is completely within your system. This is just like the forces during a collision that we don't normally need to calculate. So we do have a force of each of these on the other, which causes the overall speed to change, but because that's within your system and not an external torque, it can't change your angular momentum. So that's how you think through one of these problems. You would then actually do out a calculation, and this is just like a collision, but again, it's rotational. So angular momentum and the fact that it's conserved for an isolated system can be helpful in these sorts of situations, or like the figure skater, when you have a configuration of the system changing so that the angular momentum is conserved, but your moment of inertia changing your angular speed.